ITER week. Good morning. I am Shishir. Uh, I have been in the ITER project since 2007 till the end of this financial year, and I have seen it start from kind of scratch. So the objective of the ITER week is to give you a little close-up look at this project because you have seen the panels, and I'm sure you may have seen the videos where you saw the purpose of the mega science and also uh, the introductory talks on ether and plasma. So what I will do is I will kind of take you on a quick tour of history and some up close things which you may not have seen in those earlier videos, and give you a flavor of the challenges. And the idea is that I will end at the ether joining by itself, but the next talk, which is about ITER India's deliverables to ITER France and how we are going to meet those challenges and what are we doing about them, will be covered in the next talk by Dr. Mahendrajit Singh. So, although I am putting the word challenges here, it's more a teaser. The real stuff comes, say, half an hour or an hour later. And so again, thank you for coming here. It's a working day. I know it's not easy for people to leave their work and come here. So this blackboard stuff is very interesting, and this is because this sentence was written in 2012, and so the word mega still winks at me because we did not know this mega science exhibition would be held there. And so this is a part of a presentation, a series of presentations we had made to the government in 2012 onwards till, and we continue to make. So why this is interesting is uh, we are demonstrating. We're not really producing energy on a mass scale, and it's virtually limitless because while deuterium, which was made during the Big Bang itself, is plentiful. Uh, the tritium has to be made from lithium, and there are vast reserves of lithium, but of course, everything is limited there. So that's why it is virtual. It is safe. I will tell you why it is safe, and it's of course environment friendly, and because of a number of reasons. Because it doesn't burn the carbon-based fuel, and so it's from the hydrogen isotopes that we will. So let's see, why do we do this, and ITER particularly, how did it start? So there are 5 points here. It's first of all a new source of energy. That's very important because you look at our needs. We are producing at our installed capacity is around 200 gigawatts today, roughly, and we added 50 gigawatts in the last 5 years. And how much do we need? So, if we go by a normal development index uh, and compare ourselves, okay, let us say we want to be just on par with the world. So, you add up the total electricity production and then take average and per capita. So, it turns out that you need almost 800 gigawatts. So, we need to add 600 gigawatts, which is a very hopping figure, 300% increase. Just the increase is 300%. And if you go at the rate of 50 gigawatt, you will need several years to do that. By then, the world would have advanced far more. So the gap is, I mean, tremendous. And we must do everything possible to add to the energy sources. And even if you add up all the renewable potential, the wind and the solar and the hydro, it won't add up to that. So we need India needs particularly large resources because it has large number of people and the country is basically hungry for power. A lot of infrastructure gets decided by how much power you produce, and the power decides the price of various things. Our You can see the tremendous dependence we have on the oil imports. Almost more than 50%, much more than 50% needs to be imported. So we can be easily taken to ransom. Okay. So while we don't need to get into that, it's important to know that we need to find out whether there are sources of energy which are much better geographically distributed and much more geopolitically better place for us. It's good for environment because it has less radioactivity. It is safe because the reaction has if you go on increasing the temperature of the fusion plasma, it can turn itself off. It's not a thermal runaway like it can happen elsewhere. And the fuel is abundant because it is predominantly seawater and a large amount of lithium deposits. Lithium can also be obtained from certain seaweeds also. And it is proven in the laboratory. It was done in 1994 in the US in the tokamak fusion test reactor and in EU in the Joint European Torus. It's actually 1993 and 1997. And so these were the powers produced. Of course, this power was produced um, by putting in a lot more input power. So obviously, these were not really the reactor plasmas, and we had to put in more power to produce those 10 megawatts. But that is okay because one was not using the real fusion mixture of 50-50 and so on. So if we look at the next slide, the progress of fusion devices has lent credibility to it. And you can see this graph. This is a bit okay. Let me just tricky to understand. So on the y-axis, you have the experimental confinement time. Confinement time is the time up to which the energy is confined in the plasma. If you turn off the power source to the plasma, how much time does it take for e-folding of the energy content within? That's the experimental confinement. On the y-axis is a very interesting number. That's essentially the confinement time, but it's by a scaling law. The scaling laws have been derived out of a combination of a tremendous theoretical insight by people like Kadomshev, Copy, Marshall Rosenbluth, and so many other plasma physicists in the past, and a large number of experimental data in different configurations. And so, if you plot uh, the theory which is on this side, let's say, and the experiment, it's kind of falling on a 45-degree, which means that you are doing good. And if you look at this curve here, these points here, they are basically very small tokamaks of the order of 1 foot kind of a measure radius. Whereas if you go up, you're going up in the size of the tokamak. So larger the size, the larger is the confinement time. And there is a reason for that. We'll come to that in a moment. So you look at this, for example, the blue curves, which are basically orders of quarters of a meter or so. And finally, you look at these red, dark red things, which are basically from the jet tokamak, joint European torus. And if you look at this little black patch here, this is very interestingly the CMOD. The Alcator CMOD is a very interesting. It was a very interesting tokamak in MIT, and it was basically copper coils, but all the copper coils were like there was not a conductor; it was like a sheet, and those sheets were immersed in a liquid nitrogen bath, giving that copper a tremendous ability to carry high current. So this tokamak, this black dots here, is the largest field ever produced. It's 8 Tesla in the center, and even ITER produces only 5.6, and 8 Tesla by resistive coils. It's just phenomenal. But it had, naturally, it had a very small minor radius. So unfortunately, the product of the minor radius and the field is still modest, and so it can't really go up high in confinement time. But all said and done, it did introduce a wonderful diversion into the statistical regression analysis of the data, and thereby brought even more robustness to the scalings. So this is ITER. That's where the ITER stands. 3.6 seconds, order of 4 seconds confinement time, which is very high confinement time, because in normal tokamaks, small tokamaks, you have orders of a millisecond or a fraction of a millisecond, or of the order of at best a fraction of a second in big tokamaks. So why confinement time is very important is because if we take confinement time as some x tau and multiply that by the power that we put in, that gives us the energy. Confinement time into power gives us the energy that is into the plasma. And it is this energy which is kind of distributed over the random motions of the particles, and it's going to cause fusion. So we need as high a confinement time as possible. Here on the left is a picture, a cartoon of a tokamak, where what you see is these bangle shaped or D shaped coils here, and the plasma at the center. And what you see in these green arrows is like the field lines. And the basic physics is rather simple. There is a magnetic field. The magnetic field does not allow charged particles to wander away from the field. It just goes circulating around the field. Of course, it goes all over as the field flows. So as long as you make the field line circular, there is no problem. At least that is how one would like to think, but it's a little deeper than that. If the field lines are curved, then of course there is a drift of the particles, because the field particle orbits don't close on themselves. But all said and done, if you have a helical field which is sort of self-compensating, you have a very good configuration. In fact, toroidal magnetic field is one of the best configurations you can have. It is the only solution of this so-called divergence B equation where the field lines do not go to infinity. So there's a lot more deeper mathematical stuff there, but we don't get into that. So if we look at uh, having seen this need of ITER and the need of energy and the fact that you have a credibility in the ITER, of course, is the next logical step. It started in 1986. Of course, it was more out of a combination and a need to integrate, the two polar powers on a common platform, from the Cold War to a warm collaboration. And then it finally, eventually, in 2005, 2006 actually, in the Elysee Palace in Paris, there was a signature on the ITER agreement. The ITER is a very complex affair, and I will tell you that, but basically there is a broad intergovernmental agreement called ITER agreement, and then we all follow that agreement. So let's see, what is this ITER project. So in a simple word, it's a fusion reactor being built in France by many in-kind contributions from different partners, and it is the first of a kind. It's a global endeavor, basically, and it's more complex because there are too many governments participating, etc. But uh, being first of a kind makes it very unique in the sense that there is no reference to draw from. You don't have benchmarks, you don't have established factories and facilities, and you have to establish them too. And when you do project costing, you do not normally include this background additions and value additions that happen to your own country. So it aims to produce 500 megawatts of thermal power by using 50 megawatt of externally injected power. And there is a lot of confusion on that, so we will spend another half a minute on that. 500 megawatt is the fusion power produced. 50 megawatt is a power coupled to the plasma. That doesn't mean that we are putting in 50 megawatts, let's say, on a transmission line there. There's an electrical efficiency, there's a conversion efficiency, and so on. So for 50 megawatt is the coupled power, and if you ask me, if you take 50% of the efficiency, then one is actually at the electrical switchboard, one is adding almost 100 megawatts of power. So, but the amplification factor, the figure of merit, is defined like ratio of output power to input power. Very simple. And so that's how this factor of 10, figure of merit, or capital Q often called, is written here. It is administered under a joint implementation agreement called JIA. It's available on the web. You can Google it. And IAEA is the depository of the agreement. The DG of IAEA is the depository. There are seven parties written in alphabetical order here. And EU is the host party. And within EU, France is the host state. And so when we build a reactor, we have to obey the laws of the land there. So the French laws and the various French regulations also apply to it. uh, and it's being built by in-kind commitments. So ITER has a very curious structure, and so no one will ever find out about the real cost of ITER because there are so many in so many currencies. So the simplicity is that ITER adopts is that there is a ITER unit of account, IUA, and when the ITER was being designed, different partners had calculated and converted the cost of their procurement or proposed procurements onto a 1989 US dollar value, and it was benchmarked against that. So that benchmark has remained, and so everything is calculated in IU, and we will return to that in a moment. Here I'm saying 46% and 9%, which is also an approximate number, and we will see it more accurately later. The apex body of the governance is called ITER Council. ITER Council consists of members from different parties and representing their governments. So, here is the reason why we must do this. Because, first of all, it will leapfrog the domestic program. We are going at a certain pace, but if we participate in ITER, we are exposed to new technologies, new industries, different labs on a common collaborative platform. That makes it easy for people to interact easily and find out what are the good solutions to the various problems. It is overall economical because it is so large that no single country would have been able to make, for example, the superconducting wires needed for ITER in one go. You needed almost six or five different production units spread over all over the world, and they had to follow the common quality and specification norms. So it is compared to and being first time built, whatever cost it is, we end up paying roughly 10%, but we have access to 100%. And this is true for everyone. It's not just for India. It's everyone is going to have this amplification here, except the EU, where EU pays for almost 46% of the cost. Early realization of fusion technology is essential because there are many spin-offs possible. Energetic neutrons from fusion can be used to decimate the high-level radioactive waste. They can be used to convert thorium into uranium. It can add to a time advantage to thorium utilization. While we are already going in that direction, always a helping hand will be very useful if we had large number of energetic neutrons. So let's see what was the background work here. If we look at the background work, you can see the address, because you won't be able to read that, so I have expanded it here. So this was the statement by Dr. Kakodkar in 2003. We are watching recent developments in progress of ITER and very keen on opportunities of participation. Then this is one of the DAE's document here, and so you can see here a press release kind of thing. India has expressed its interest in ITER and willingness to contribute, and the US will consult its partners. This is July 2005. And so in 2005, when Professor Kaur was the chair of the International Fusion Research Council, here is a summary by Werner Burkhardt, DDG of Nuclear Sciences Division, and it says Professor Kaur prepared the report on behalf of the IFRC, reflecting members' personal views on the latest achievements, including magnetic and inertial confinement scenarios. And so it describes the progress, and particularly with ITER as a possible partner in the realization of self-sustainable burning plasma. The importance of socio-economic aspects is also covered, noting that the applications of plasma science are of broad interest. Report addresses topic of plasma physics versus understanding of choosing better coatings, cheaper light sources, improved heat resistant materials, and other high technology. So you can see that at this stage, one is already considering various applications in the interim period, and as the technology advances. So let's try to understand. We often encounter this question: why this thing is so big? So if we look at that, the design of ITER is based on ITER physics basis, which starts from 1992, and there are many solutions to various problems which plasma physicists encounter. And then it is also based on a consensus across parties on the safety principles and design criteria, that in case you do the ITER operations, what will be its impact on the environment and how to contain that. And then, of course, there is a cost target. And this is a ITER final design report, and even this is all available on the web. So let's turn to a little bit of analysis. The thermonuclear fusion reactions between deuterium and tritium produce an alpha particle, which is 3.5 MeV, and an energetic neutron, which is 14.1 MeV. And the reaction rate at 10 keV, which is the fusion temperatures, is close to 10 to the minus 22. So, if we want 1 megawatt per meter cube as a standard power density in a reactor, then we need to have a density of the order of 610 to the 19. This is easily one can work out by. It's not even you can do it in your head also. So at 20 keV, this implies the plasma's outward pressure, because you have confined the plasma, you have density and you have temperature. It's like basically like a gas, NT. So the pressure, outward pressure from the plasma will be close to zero point 0.4 megapascals. Now, excuse me for the mess up of notation here because of this particular font, but its M is capital there. So, if we then say that how do we now stop the plasma from coming out of the vessel or going away or dissipating away? You want to keep it in one place. And so to do that, you must put a counter pressure, an inward pressure coming from the magnetic field, and that magnetic field pressure would be of the order of, the field would be required will be of the order of 5 Tesla. Now, how does a field produce pressure? That's easy to understand, because you can see that if you balance the pressure forces with the magnetic forces, which is say current density multiplied by B, and then use one of the nature's laws, curl B is equal to J, which is basically like saying that fields produce currents, currents produce fields, and they both influence each other. You will see that you will get uh, the expression will look like the pressure is like square of the magnetic field, and this is a very important finding. If you use the force balance and the Maxwell equation, you can show that the pressure is kind of equating itself to the square of the magnetic field. And this ratio becomes very, very important. Pressure upon the square of the magnetic field is actually called beta, very important parameter in plasma. But anyone would be able to derive that very easily. So if we then say that there is a limiting pressure beyond which the plasma will escape the magnetic gauge, and that limiting pressure is taken, then you will need a field of the order of 5 Tesla. Now, if we combine this with these phenomenal insights that have been developed over the last few decades and the dimensionless scaling arguments of plasma confinement, where the product of the minor radius and the magnetic field, the V is capital here, then we can easily see that the plasma must be of the order of 2 meters because magnetic field is of the order of 5 Tesla and you must meet this number 10. So this all came because of this A, that is the minor radius times capital B, the field product should be of the order of 10. And producing large magnetic fields over a large region requires superconducting magnets. And today we are at the cutting edge of technology where niobium, titanium, niobium 3 tin, these are the materials being used, and they give you orders of 10 to 12 Tesla maximum. So the key point is that since the fusion power goes as b raised to 4, because p goes as b square and the fusion goes as p square, so it goes as b raised to 4. Even a minor improvement in the high field superconductors can be dramatically bringing down the size and the cost of the reactor. And this is what is happening today. There are rare earth based barium and other superconductors coming up, and they will be taking this far more. And so we will be able to meet this A times B of the order of 10 by going up in B and going smaller in A. And so the cost of the reactor, so to say, therefore, is decided by the minor radius. Let's look at the evolution of this project. So if we get close to the project and ask ourselves what was it at the time of signature, then some design issues were not fully resolved. They were site specific and safety regulatory aspects were not integrated, obviously because no one knew where it will be built. When the ITER negotiations were happening, they were happening on where it will be built, and obviously those local laws could not have been integrated into the design. So there was a generic site safety report, it was called GSSR. And of course, the project execution bodies like ITER organization or domestic agencies had not been formed. It was much like a green field where nothing exists. You have to create the organization, you have to recruit people, you have to build your various departments, you have to prepare designs, then you have to start procurement, etc. It's not some ready laboratory where institute where you just have a team ready to execute and all that has happened is let us build. It wasn't like that. So design changes have come from a review. This is the first of a kind project where obviously there were no precedents and there was a lot of improvement in the scientific and technical understanding since 2001. That was the last time the design was reviewed. So in 2007, when the design was reviewed uh, by almost 150 experts, and it lasted for almost 2 years, uh, the various outstanding issues were consolidated into some kind of issue cards and then finally into design change requests. And so that is one pass. Second thing is when the contracts were awarded subsequently, there were issues like can we manufacture that? If you look at some of the ITER components, they are so huge that you cannot put your arms around a column where a magnet is being made. So you need to weld those kind of thicknesses, and you need to be sure that the weld has penetrated all the way down. So you need to devise new techniques. You have to meet new codes and other conditions. So these were the things that brought in some more changes. And then there was in 2011 this Fukushima incident where the regulators did not want the design to proceed and they wanted to look at reopen the design and make sure that the collapsing condition, the crash conditions were again strengthened, and they went far beyond, of course, the margins, and so one had to redo some of these calculations and rebuild some of them. To put that in a perspective, you can see this thing here. On the left hand side, you will see a picture of, on the top is the number of changes that have happened, and on the x-axis you will see what is called a DA, which is a domestic agency. Domestic agency is nothing but an organization in a given partner country which is executing ITER. So this is China, Europe, India, Japan, Korea, etc. And the height of these columns here tells you how many design changes have significantly affected you. So you can see, of course, the EU has many more procurements, so obviously that thing is taller than ours. But you can see that it has been broadly here. So almost hundreds of changes have impacted. These are major changes. Now there are 1,000 changes, but we are looking at 100 major changes. At the bottom, you will see changes affecting the main systems. Now, here on the x axis, what you have is the systems like cryostat, the cooling water, the vacuum vessel, the magnets, the cryogenics, and so on. And you can again see that everyone has been impacted. And interestingly, you can see this, for example, this cooling water system here is kind of tall compared to others, because what happens is that the plant systems get affected by everyone upstream. Cooling water is going to provide water to, electron heating, ion heating, etc. Any one of those changes are also going to affect the cooling water system. So again, you can see some kind of a balance. It's not some system that has been dramatically. Everyone has been affected. Every system has been affected by the design change. And again, you can see almost hundreds of changes here. On the right hand side, you see a cross section from one of the computer models of the building. You have removed the walls here, and there are 7 floors here actually, if you look at the 60-meter tall, and you can see the terrific density of the piping, the components inside those buildings. So there are many interfaces, and if you don't have clashes, you will be lucky. So you need to resolve them. You need to do the detailed designs, and so there are, of necessity, as you go into details, there will be changes. So there were changes, and those changes were happening. So as a result, initially the progress remained slow, drawing a tremendous amount of criticism around the world. So if you look at this, you see the agreement in 2006, the excavations in 2011, the seismic pads. The entire ITER is sitting on a some kind of springs. Uh, Building also sits on some kind of springs, you can say. In 2012, seismic pad. The license, which is obtained by putting out all the details of the reactor in public, as per the French rules, and one has to make comments and collect them and defend them, and then finally the government agrees to give a license to build a nuclear reactor. In 14, you can see the slab being poured. It's called B2 because it's a base mat, and then there is a base mat 1, and then there's a base mat 2. And finally, you see the early buildings of 2015. I will not show the rest because they will come up in the next presentation. And the latest, is all available on web. It's a live cam. You are encouraged to go to the www.iter.org, and you can see live construction directly going on. You can see people moving, stuff like that. So initially the thing was slow, but then it got speeded. And if you look at the how the changes got implemented, you can see that as the time progressed, the implementation started kind of here. So when the design and got implemented, changes got implemented in design, you can see around 12, 13, and that's the time when things started picking up. So this early period that one has in this period is mostly the preparatory activities, and the setup activities, and that's not really, so to say, the start of the project, as per a definition of the pour of concrete. So, what is this 2016 baseline? It is basically the promise by the ITER designers and engineers in 2016 November that they can build it. It has certain risks, of course, uh, assuming that various things go smoothly. The construction phase would last till December 2025, and then operation will go till October 2037. Then there is the deactivation phase and a decommission phase. You may have some extensions of the operation phase depending on the agreement of the government. So that's the target, and a very challenging one. At that, it is just 6 years from now, and but ITER has right now close to 60, just a little over 60% progress in construction. So ITER is not just a scientific and technological challenge. The third crucial element is the unique management challenge that it embodied in its very incipient stage. At the very early stage itself, this got built into that. And if we look at that, it's shared among seven partners. So, more accurately, the European contribution is 5 by 11, another six partners contribute 1 by 11 in each, and each work package has a credit value, and that needs to be earned by the partners. And if you look at the partners and the systems, you will see that system is also distributed among various partners except the buildings. You can see this building, everyone is nothing here until you come to EU, and here you can see is 400. Since 400 is what? 400 is the kilo ITER units of account, which is associated with the construction of the building. It's basically a figure which tells you how much credit is for the building, how much credit is for the vessel. And once you supply that stuff and you earn your credit, you are done. Basically, your obligations are over. It's a way of measuring earned value in some sense. But it also has a interesting relationship to via the 1989 US dollar to euro. So you can see different people are contributing heating systems, external auxiliaries, internal auxiliaries, machine core, which means the blanket, etc. And you will see more of that later. The international organization and the domestic agency have the following roles. The role of IO is to design, specify, monitor the progress, quality, etc., and integration, commissioning, etc. Whereas the role of the domestic agency is to complete the design, complete the procurement, manufacture, supply, etc., provide all the documentation, and particularly monitor the progress of the suppliers. So we have this strange stuff here. We have one project, we have seven agencies and seven governments, so to say, and hundreds of work packages, thousands of contractors, and millions of components. And for every major system, we have this complete cycle. We have to design, develop, prototype, test, manufacture, test again, accept, integrate, commission, and operate. A long cycle. And there are several systems like that. So that's why it is a global challenge, even for managing documentation, communication, tracking. And so, if we look at uh, what ITER is, it's a mandate for burning plasmas. I mean, ITER will be the first ever device to strive to reach burning plasma conditions. It's the holy grail. No one got there so far. And where energetic alpha particles keep the plasma hot enough for burning on its own. That's the dream. ITER produces alpha particles, they are at 3.5 MeV. And they are all at 3.5 MeV, which means they are non Maxwellian distribution. It's away from thermodynamic equilibrium. And using this fact, you might just be able to use that fact As it relaxes into thermodynamic equilibrium, you might be able to create heating, current drive, and things like that out of that distribution. So there is a strong potential for those alpha particles to deliver their energy, deliver the necessary momentum via waves into the plasma, and keep the plasma hot and going, because you need current driven also in the plasma. It will be the only device to demonstrate that tritium, which is the fuel gas, can be bred inside the reactor. So ITER has a test module where you put in some lithium salts, and the neutrons from ITER will convert the lithium into tritium, and you will detect it, and that will be the proof that it will all work. Because when you make the full reactor, the demo reactor, you need to cover the entire reactor with lithium blanket, because where will you get the tritium from? You have to produce it within the reactor itself. And it will be the only device to demonstrate the technological performance of high grade heat extraction. This high grade is important. You know, the thermodynamic efficiencies are connected to the uh, higher and higher temperature give you better and better efficiencies. And so, if you can take the heat from the tokamak reactor, uh, and the higher the temperature that you take it, the better are your chances of having high efficiency conversion to power. So, with these conditions, the fact that you have a unique opportunity, there is a need to be with it, to do it, and to utilize its knowledge. And what happens beyond it? A demonstration reactor. The answer, of course, is in the very objective of ITER. The ITER was built for demonstration of fusion energy. So once you demonstrate that, you must build a demo, because you must build your own electricity producing reactor to satisfy your needs. And so while we wait for ITER to generate the results, which is a long uh, duration from now also, we must keep ourselves ready by carrying out various technology development projects aimed at the currently sized demo designs. Currently sized demo designs are also similar to ITER. So, if ITER says that we need 70 megawatts of heating power, we should be targeting, are the systems capable of doing that? If it is saying that you must have a 5 megawatt per meter square heat handling capacity, we must start building those systems. We may not build them on the same scale as ITER, but we must have a readiness, because it is the technology readiness which made many things possible. You recall the launch of Chandrayaan in a short duration. That was because a large number of those technologies were already available. So you get an advantage of opportunity and cost if your technologies are ready. And those technologies could be useful to other demo designs too. Because by the time you complete ITER research, you might have found a new, better superconductor, more compact reactor designs. So those technologies, and for those compact reactors, you will need even more heat handling capacity. So you need to do that. So there is demo. There is no question about that, because you are doing investment in ITER, and if it works, then you must be ready to utilize that, because beyond ITER, you won't have that kind of so easy sharing of information. It is heading into a commercial direction. So we don't want to lose that intellectual property advantage. Secondly, the demo designs may change as new information arrives, like as I said, superconducting magnets, heat handling materials, compact designs. So, for the investment that one is making, a readiness is essential. So, with that, I would like to close session. I think one slide which might be of which I did not touch upon would be this. As we send the components to ITER, uh, they are all going to this harbor here, and from there they go on a barge, and then finally, using a land route, they are reaching ITER. And there are very huge components. So the local governments have taken care and that the roads are wide enough, that there are no bridges and stuff like that. So it's a heavy haul itinerary of ITER components. Very interesting to see that. Currently, India tops this list because we belong to the early delivery systems. A large number of our systems are reaching there, and we have quite heavy components, as you will see in Mahendrajit's talk. So thank you again, and I think that this is a very beautiful picture I have taken. So hopefully one day. Thank you very much. Questions, if any? We have, in terms of our deliveries, we have, in terms of practical terms, the closure of the cryostat has to happen in 2024, and that's the cryostat is a place where all the components go in. And so, for the cryostat is just a one big vessel, as you know, but a large part of that vessel is already at ITER site, and you can say one part is already handed over, other part will be handed over soon. So we will be done with uh, at least three major packages in maybe in just about 2 years. One is the entire cooling water system will be over probably this year. The in-wall shields, which is one of our procurement, will be over by next year, and a good part of the cryostat from the Indian side will be over by again early next year, and at French side it will take some time. That's because they have to lift it as per the building. So there is with those three packages done, we have cryogenic lines, which will also be over by 2022. So we see ourselves doing well on time, and if the vessel which is being done by other partners and the magnets arrive in time, then the assembly should start in 21, 22 of the various components, and the commissioning of the plant systems is going on. For example, building 61 commissioning, which is the site services building, this commissioning I think it just happened a few days back, and there are some more systems being commissioned. So site is very busy today. You will see, if you go to the site, you will see hundreds of people and items all over, trucks moving. So I think the next few years will be very exciting in construction. Yes, ITER has a very unique inertia. So whatever for whatever reasons, even coming out is not easy. So so yeah, it has. Yeah, India has received its. No, India has approved its cost and schedule baseline in July 18. The new revised approval in July 18 gives India the required resources to meet its commitments, and that's good enough for us. We will be within that time. Okay, if someone else gets delayed and because of that we are not able to install our component, that's a matter between the ITER organization and the partners to decide. But fundamentally, there is no issue, uh, except that you hear that ITER organization's own contribution, so-called cash contribution, which comes from our partners. On that, people have to resolve some issues, and then it should be through. You often hear the partners saying that they won't be able to support, this is too expensive and all that. But I think that if you look at it in a comparative scale also, it is okay. It's not so astronomical. If you look at the amount of effort involved and correlate that with cost, it finally is a balanced situation. It is the complexity of its management which cause a lot of time initially to adjust to. Other than that, now the processes and systems are in place, so it's a matter of time now. No, I think the ITER had a fair negotiation of our sides. I think there were other parties like Canada, Spain, Japan. They were all competed for that. The advantage was that once you locate ITER, then of course you have to spend 45%, but then you get the advantage of the system being there. So there was a competition, and France won it by competition. And second reason is that in Europe, France is very strongly placed in terms of nuclear power. A good part of its power comes from nuclear reactors, and so it has that all that infrastructure and the necessary mandate. So ITER is kind of located also near the French nuclear sites. Yeah. Yes, tri alpha. As far as fusion reactions are concerned, there are many different ways in which they have been produced. Even the National Ignition Facility, uh, the laser produced plasmas, they've also produced them. But what happens is that uh, the conditions in which they are being produced have to be scalable to a large size or large power. So here one has to see how much is the energy one will invest in the beam accelerations and stuff like that, and how much power, how much you need to do, how many reactions you need to do to get a reasonable power. Because finally, you see, you need to have a system where there is some blanket uh, surrounded by a coolant, and that's the coolant which is going to go to the turbine and the heat exchangers. The reactor designs are like that. There is no direct conversion to electricity. So you need to have conceptualization where uh, a conventional heat engine can be created. Even in the case of laser, you will need to have several pellets being burnt per second, and even that is not so easy because you need to have that whole ram, which is a indirect drive. So the lasers produce melting in the X-rays, and the X-rays produce the implosion, stuff like that. So while you may produce fusion in isolated, localized conditions, you need to see its scalability to a conventional power reactor. And at this moment, uh, amongst the accelerators and other toroidal machines, only tokamak survived, because only uh, the bigger you make it and the more plasma current it has more confinement time, and therefore it has a possibility of reaching the fusion temperature. So that is how it is there. At this moment, there is no candidate which can outperform tokamak. Although there are some very good uh, candidates coming up, which are called stellarators, as I said, and the advantage they have is that they don't have plasma current, and therefore they don't have plasma disruptions. But they have not reached the kind of temperatures which tokamak has.